Okay, good afternoon, everyone. My name is Mahmood Ebadian with Biomass and Bioenergy Research Group at the University of British Columbia in Vancouver. First of all, I would like to thank BIC for the opportunity to present the result of our study that we have been doing with BIC and Co-op, and of course, I've been working closely with Galen from AGCO to sort of create a big picture of the logistics system, how it's going to look like at the end. And this model that we have been using in the last 10 years is not going to be the final solution. So it's more about creating a discussion and provide some insights so we can actually move forward and make a more informed decision. Like that's the final goal of a decision-making support model. Regardless of the type of the industry, I guess the big challenge in every supply chain is trade-off. And because we are talking about different players, they have to work together. At the end of the day, they want to meet the specification of their end user. And of course, at the lowest cost with the highest quality and to meet the quantity and delivery time. And when you look at the biomass supply chain, we have actually a lot of trade-off points in the system in terms of you can improve the quality, but you have to pay for the costs. Or you may not touch the biomass, you want to deliver it as it is, but that comes with a lot of handling issues, pre-treatment, pre-processing of biomass. And I guess biomass supply chain is on the bottom of the curve right now. Here we have to balance out the efficiency and effectiveness of the system. Efficiency about how to use the asset we have, and effectiveness is about how to meet the customer's specification and requirements. And we have to come up with better solution to actually move toward right top of the graph, the point that we have high efficiency and also high effectiveness. So one of the biggest challenges is the biomass. It's still with, like many companies, of course, they talk about they know how to treat biomass. But when you look at the history of the bioeconomy, we see that most of these bioprocessing technology, they still have lots of issues with handling biomass, storing biomass, and of course, pre-treating biomass. And it's more about physical properties and chemical composition, right? It impacts the type of the equipment you want to use, the size of the equipment. It impacts the storage configuration, and also it impacts the pre-treatment. I guess that's now the bottleneck that the industry is going through. They are delivering biomass maybe at the right quantity, but the problem is that they cannot handle and also they cannot pre-treat biomass efficiently and effectively. And also biomass supply security is a huge challenge, and also the price stability. I mean, from my perspective, now we see that we have been able to develop enough knowledge to deliver biomass to the facility. But as new technology are coming up, there might be actually competing uses for biomass. Then we have to deal with the price stability of the biomass in the long run over the lifetime of the facility. So one solution to sort of understand this trade-off and to identify this trade-off is, of course, modeling. And that's what we have been doing the last 10 years. So what we have been doing, we have developed a model, we call it IPSAL. It stands for Integrated Biomass Supply Analysis and Logistics. And actually, probably you know Dr. Shahab Sukhansan. She has been working with Oak Ridge National Lab, the U.S. Department of Energy. He developed the model in Oak Ridge Lab, but we have been working together to sort of, again, bring this knowledge that we are developing in industry and create this engineering equation. So it's not an economical model, it's a combination of engineering equation and of course economic equation. And we look at from very beginning of the supply chain, from either could be a biomass, like could be a farm, it could be actually a forest stand, because we look at different types of biomass. And till the end of I would say at the gate of the bioprocessing, because handling of the biomass at the facility is also a challenge and it could be expensive, like grinding or drying biomass could be very expensive. So we look at the entire supply chain to sort of understand what would be the cost and what are the trade-offs. If you want to improve the quality, what would be the cost, and can the bioprocessing facility pay for that cost? Is it really a value for them? Is more a cost for them? And Sorry, I'm just going back. So this is a general structure of the model. So we actually look at very detailed data. So it's not a spreadsheet that we just get the average values, put in the spreadsheet, and then get the output, because biomass supply chain has a lot of dynamics, has a lot of stochastic parameters. We look at the weather data because the weather data impact the harvest window. It also impacts the moisture content and other qualities of biomass. So we get the weather data to sort of estimate what would be the moisture content, for example. And also we get crop data, storage data, field data, the location of the field, and also the size of the field. And then we feed these input data into it's a more simulation platform we are using. And then get variety of output, including the cost of delivery, and dry matter loss, what would be the estimation of the dry matter loss in the system, energy input we need to run the equipment, so we have to use energy, and also what would be the associated CO2. So that could be also used in a life cycle analysis. And this is the one that we have developed specifically for this project, for the Sarnia project. And as you can see, first we have been trying to use the recent equipment has been used, especially in U.S. For harvesting and collecting corn stover. And I get a special thanks to Galen helping me to get the most updated data from this equipment. So we have field operation, of course. I would say that's a push part of this system, because we need to harvest as much as biomass possible in a short period of time. And either you want to deliver it directly, maybe during the harvest window, but you need to store it. I guess that's an option that you have to consider in your supply chain. And so that's part of the push system. Everything should be harvested. I mean, we need to harvest sufficient volume of biomass. And then the second part is we have just-in-time delivery, which happens during the harvest window. And then we have the storage option. And this part, I would call it the pull part. This pull part is more, depends on what is the daily demand of the bioprocessing facility. Then you pull enough biomass to meet the feedstock requirement of your bioprocessing facility. So it's a combination of push and pull system. And we did it in order to simulate the real system, so we can come up with more accurate numbers. And we have applied actually the model to different real case studies as I mentioned, the last 10 years, including both forest biomass and also agricultural biomass. In BC, we have worked with several wood pellet companies to understand the logistics system they have, because they are actually we are looking at the international supply chain, because they collect forest residue, they pelletize it, then they transport it to the port, then from the port they transport it to European countries. And in 2009, we worked with Iogen on their facility in Saskatchewan using wheat straw. And in US, we look at the DuPont facility logistics system, and also in North Carolina, we look at a miscanthus logistics system for, of course, using miscanthus for Kimtex. Of course, that's a proposed ethanol plant in North Carolina. And in the last 2 years, we also work with OPG, just do an analysis what would be the cost of corn stover if we deliver it to the Lambton power plant. At that time, OPG was interested into this study. So let's just take a look at the Sarnia project. So we had 2 meetings with BIC, with Co-op, to develop a base case scenario. Right? So we are not, the final goal is to find those logistics scenarios that they have the lowest cost, but we decided to start with the base case scenario, so in order to understand the system. Then from there, based on the brainstorming session we are going to have in the future, we move from this base case scenario to this optimal solution. And we started with 4 main counties of Huron, Lambton, Kent, and Middlesex. In that these are the regions that they have the highest potential for corn stover production. It was really challenging to get data at the farm level, so that's why we decided to collect data at the township level. And the reason is that we want to estimate the real transportation costs and the location of the farms, again, in order to estimate the more accurate numbers at the end of the day. That's why we were really interested to collect the data at the lowest level possible. So then I'm not going to go through this, but these are some of those main assumptions we developed, again, based on the brainstorming session we had for the base case scenario. And the main assumption is we look at 2 different facility sizes. One of them was 175 dry ton per day. And the second one, which was the largest scale, was 860 dry ton per day, in order to see what would be the supply chain for both of these facility sizes. So these are some of the output we got. In terms of the average corn stover yield was 1.72 dry ton per acre. That's the average amount we got. And also our estimation showed that the supply radius for the smallest scale would be around 45 to 65 kilometer. And for the largest scale is around 120 to 140 kilometer. And you see there is a range because we have variation in the system. We have variation in the corn stover yield and the location of the farm. So that's why we don't have a fixed number. We look at the variation. And that variation actually could be really valuable, for example, for BIC to see what would be the worst case scenario, what would be the best case scenario. And again, they can make a more informed decision based on what is the wide range they are getting. And in terms of how much biomass we need to meet the demand of this facility, considering the dry matter loss. So we have about 12 to 15% of the dry matter loss from harvesting to the delivery to the facility. And we came up with the number about 75,000 dry tons of corn stover for the small size facility, and about 370,000 dry tons of corn stover for the largest scale. This is the amount we need at the field level, not delivered at the facility, because we also have the dry matter in the system. And in terms of the harvest area, the maximum harvest area would be for the smallest scale is about 43,000 acres. For the largest scale is about 220,000 acres of corn lands we need in order to meet the demand of these facilities. Delivery costs, you see the details of the delivery costs. Probably the most important one is the total delivery cost. For the smallest scale, it's about $74 per dry ton. But again, there is a range for that. It depends on, again, the worst case scenario, the base case scenario. This is the average value. For the largest scale, is about $83 per dry ton. And of course, everybody might expect that the most expensive operation are transportation, about 30 to 40% of the cost, and baling operation is the next one. So the total, again, as Charles mentioned, that depends on the bushel per acre, but that could be something from 4 to 5 dry ton per acre. That's a gross value. And then you leave about 4 dry ton per acre left behind. So at the end, you have about 1.5, 1.7 dry ton per acre. And so we have 2 storage options in the system. One of these temporary storage at the field site. And you use that storage only during the harvest window because, as I mentioned, that you need to harvest biomass and you have a short period of time. So at some point, you might need to harvest a portion of, store a portion of your biomass temporarily at the field site. And you see how the biomass is increasing. So we assume that the start of the harvest season is mid-October. So you see that the biomass storage is increasing. But at the end of the harvest season, then we remove all of that biomass from all of the corn field. That's for the base case scenario. We assume that right after the harvest season, we need to remove biomass. But in reality, when you look at DuPont or Poet or even the Abengoa, actually they have contract with for some of the farmers to leave a portion of biomass for for a short period of time, maybe by end of the February, to remove biomass. So there is an option for the bioprocessing facility to use this short-term storage in order to reduce the storage costs. And of course, it's also important to manage the loading and transportation equipment, because if you want to remove biomass right after the harvest season, then you need a lot of loading and transportation equipment. But if you have a gap between the harvest window and the storage, then at least you can manage your loading and transportation equipment. So that was in the, as I mentioned, the temporary storage at the field site, but we have offsite storage. So offsite storage, or maybe you call it intermediate storage or satellite storage. These are basically the storage at some point between farms and the bioprocessing facility. And as you can see, of course, you might expect that the biomass storage increase during the harvest season because you need to remove biomass and then transport it to these storage facilities. And then after the end of the harvest season, you see that the biomass is gradually transported to the facility to meet the daily demand. What is important of this graph is then we can estimate how much land we need in order to store sufficient amount of biomass, so that we can meet the demand of the facility year-round. And our number shows that for the small size facility, we need about 45 acres of land to store about 50,000 dry tons of biomass. And for the large scale facility, we need about 254 acres of land to store about 264,000 of dry tons of biomass at this offsite storage. And these are just some information about the storage configuration. Again, we try to use some of the number we have in US. And you can see the size of the stack is 6 bale high, 6 bale wide, and about 60 bale long. That's the size of the stack. But again, depends on the business model of a bioprocessing facility. They might actually have a different stack configuration. And then our number again shows that, again, we look at, the storage cost is not just about the land. It's also, you have to look at the dry matter loss you have, because bales are valuable at that point. You already harvested, you already collected, you already transported. So that bale has a value. If you lose a portion of that biomass, then you're actually losing the value in the system. So that's why you need to consider the dry matter loss as a cost component. So the cost at the end is about $5 to $6 per dry ton. These costs include dry matter loss, land, and also the tarp, if you want a tarp, tarp costs, and of course the labor to apply the tarp on the site. But we didn't look at the land preparation, because as you have a area to establish a storage, you might need to do some land preparation. That's the next step. We are going to look at the land preparation for the facility. Truck loads, that's another issue for the local communities, because we have to make sure that not creating any traffic congestion, and also is not having any negative impact on the lifestyle of the local communities. So that's why we look at the truckload, and also we need to look at the truckloads to estimate how many trucks we need to meet the demand of the facility. So you see that during the harvest season, of course, you need more trucks, because not only you want to meet the demand of the facility, but also you want to transport bales from the farm to the storage facilities. So that on average for the small scale facility, you need about 27 truckloads be delivered to the facility and also to the storage site. But you just need 10 trucks for the rest of the 10 truckloads for the rest of the year to meet the demand of the facility. And that means we need about 12 trucks during the harvest season, but you just need 2 trucks after the harvest season. And the same story for the larger scale facility, but you see that you need a lot of actually truck loads and also trucks to meet the demand. And as you can see, for during the harvest season, you may need about 70 trucks just to make sure that you are removing all of the biomass from the field, either to the facility or to the storage site. But after that, after the harvest season, you need about 10 trucks to meet the demand of the bioprocessing facility. And how many, like in terms of how much equipment we need, you see that these are the number of equipment you need to finish the harvest season on time and also to meet the daily demand of the facility. And the number of equipment depends on the working hours, depends on, of course, the duration of the harvest window, depends on the size of your storage facility. All of these factors impact the number of equipment you need at the end of the day. And I would say this is quite the optimal number you need, because for now we haven't looked at the weather conditions, and we assume that all of the working day, all of the days are available for harvesting, but in reality you have probably in 7 days you might get 4 or maybe 5 days of working days. And of course, it depends on the location and region, and that's another improvement we are working on, to also consider the weather condition in the supply area to see how it impacts the moisture content, and also how weather data is going to impact the number of equipment. And also we look at capital required if, of course, this is based on the case if the bioprocessing facility or a co-op want to purchase all of the equipment. That's just one scenario, but we have the custom operational aggregators, that's another scenario. But for now, we just look at what would be the estimated capital for just purchasing the equipment and run the equipment. As you can see, for the smaller scale is about $4.1 million, and you need 15 laborers to run the equipment, and for the larger scale you need about $23 million and also 84 workforce to run the equipment. And as I mentioned, that we had a meeting about, maybe 2 months or maybe 1 month ago, what would be the next step. So we are looking at the sensitivity analysis, how these important parameters are impacting the delivery costs, and also farm participation rates. Of course, we look at the optimal scenario, which is 100%, but again, in reality, it could be 50 or 30%. So that's the next step. And as I mentioned, of course, James helped us a lot in terms of collecting the weather data. So now we have the weather data for the region, and we want to do an assessment on what would be the impact of the weather data on the dry matter loss, on moisture content, and also on the harvest window. And of course, another parameter is soil compaction. If you want to, for example, do a spring harvest, then soil compaction could be really challenging. So that's another assessment we have in our bucket list to look at, to see how the weather data during the spring harvest window is going to impact the soil compaction. And at the end, I would like to thank different organizations, of course, BIC, ACO, and COA. We have been working very closely, and I hope they are happy with our progress. And I would like to also mention that the BioFuelNet is financially supporting this project, and we also really appreciate what support they have provided our research group to conduct this research. Okay, thanks for your attention, and I would be happy to answer any question you may have.